Okay, welcome everybody, storage part 2. So last time we looked at the storage layer a bit. We learned about different devices. These devices are basically key value stores as usual. So if in doubt, say it's a key value store. We looked at the hard disks still used for backup. Like often you have external hard disks on your desktop to do backups, but also in data centers it's used. And we learned about two important numbers, which one number is the number of I/O operations per second, so random, addressing some random address on the device and fetching the data. That's called a random I/O, or simply an I/O operation sometimes as well. And then the other way to fetch data is through a sequential access, be it a sequential read or sequential write, and that's much faster. You can read way more data sequentially than you can read randomly. And I showed you these experiments, how these things changed over time. So the difference between reading sequentially and randomly back then in 1970 was like a factor 4 only. Let's switch on this one. A factor 4, now it's a factor 327, and that keeps on. So the gap is widening. So the improvement in terms of random reads is not increasing as much as the improvement in terms of sequential reading and writing. That's an important thing to consider. But again, to run your database system or run any other type of system, you probably won't do it directly on hard disks. On hard disk drive, you should be using SSDs. And we looked at that as well. So some sort of solid state disk that can be connected via the existing hard disk interface, SATA or something like that, but typically these days it's connected via PCI directly, and then you have a way higher bandwidth. The important thing to consider here is that these two numbers are kind of, you still have these numbers. For all of these devices, you have the number in terms of number of I/O operation per second and sequential bandwidth. But what's a big game changer in solid state disks is that they allow for multiple random accesses at the same time. You just don't, in a hard disk you have one disk arm, and that limits the amount of random accesses you can serve. It's one random access at the time. A solid state disk can do more at the time. And that increases the number of I/O operations per second dramatically. Okay. Today we look, and we talked about splitting up these layers. You can have multiple CPUs, multiple cores, and then you might have multiple L1 and L2 caches, stuff like that. And we began talking about, okay, what does it mean for storage? And there's an important technique that's called RAID, redundant array of inexpensive disks. And the idea here is that you split up your flash/hard disk/storage layer somehow to be supported by multiple devices. That's what I'm doing here on this slide. So here I will be using hard disks as a picture in all of these examples, but it doesn't matter. You could also use SSDs for that. You could even use separate data centers, separate servers, all kinds of stuff. Even SSDs internally use what I will be explaining today. RAID levels are used internally inside an SSD, interestingly. And this stuff, these techniques, this RAID technique is used all over the place. So this just symbolizes that in case you have hard disks, that's how it works, but it doesn't have to be hard disks. It also works for many, many other devices. And again, I will use the abstraction of a page or block. I introduced that last time. We had this mapping. Put it on the board again. We have some sort of ID, a page ID, let's call it like that, a page ID, and that maps to some sort of storage, a chunk of bytes, typically, 4 kilobytes. That's the mapping we had. 20. And here I will be talking about those pages, so these chunks of bytes. There's another term for that that's called block. So there's block versus page. That's sometimes confusing, in particular in literature. Block versus page. And it means the same thing. Both terms mean a chunk of data, but typically when you say page, you mean that is in main memory. And when you say block, you mean that's on external storage. That's why on those slides everything is called block. If you load it into main memory, all of a sudden you name it a page, but it's the same data. There's no difference whatsoever. It's just a chunk of bytes. And that's why I use the abbreviation B here for the different blocks. And I number them, enumerate them in a very non-computer scientist way. I start numbering with 1. Yeah, I'm sorry for that. That's a mistake. Maybe I should fix it on the slides. So assume you have a file you want to store, and the file can be broken. Yeah? Any file can be broken into blocks, of course. Yeah, that's what you do. Yeah? You have a file that's arbitrarily large. You split it up horizontally and say that's block 1, block 2, block 3, block 4. Yeah? And that's what I'm doing on the slide here. That's a file, block 3, block 4, block 5. 1022. Should I write on the seconds? It depends on how much I write. So here in this scenario, you have 2 hard disks. And what you're doing is you distribute the blocks round robin over the different disks. Now you say, okay, I don't store all of those blocks of that file on a single disk, but you say, aha, block 1 is stored in on that hard disk, block 2 there, and round robin. Yeah? You go over those disks. Here it's only 2 disks. You could do the same with any number of disks. There should be more than 1 disk, otherwise it doesn't make sense. But if it's 2 disks and more, you can do that. And that's called striping. You stripe the blocks across the disks. And that, of course, increases the throughput, yeah, because now when reading a file, you can read from those 2 devices in parallel. Yeah, you're not limited by the bandwidth of a single hard disk, but you can do this stuff in parallel. Let's hope for that this bandwidth gets through, yeah, through the interfaces and through the bus systems of that computer architecture. So this increases the sequential and also the random read-write performance. Why random read? Yeah, because now you can issue different random reads on the different devices. That's fine. Yeah? You can do that in parallel. And the more devices you have, the more disk arms you have, the more you can do these kind of things. Actually, there's rumors. So in database systems, there's database vendors do all kinds of benchmarks, and they optimize for certain things. And there was at some time a benchmark where the bottleneck was the number of random IOs. And price didn't matter in the benchmark. So what did people do? They added thousands of hard disks to have thousands of parallel random accesses at the same time. No one would buy a system like that in reality, but for benchmark you can do that. Yeah, and then you had all of a sudden 1,000 disk arms moving back and forth at the same time in a way different ballpark in terms of performance. Yeah. Okay, but so back to RAID 0. So this reduces the load of each disk, and you can use as many disks as you want. So here's a reference to the paper that appeared a long time ago already, in 1988 already. But it has become the industry standard for providing redundancy in data storage. And you see it all over the place. Yeah? In all kinds of computer systems, you see that. And so the general technique is called RAID, redundant array of independent disks. However, there are different types of redundancy you can do. And that's called the RAID level. The type of redundancy or the assignment strategy I'm using for this specific configuration of disks. So RAID 0 means striping. I stripe the blocks over the disks. But I could also do something like RAID 1. That means full replication. So basically, if I have for any block, here block 1, I put it on all of those disks. Here it's just 2, block 1 goes there, and there, and so forth and so forth. So basically, those disks are copies of each other. Yeah, and again, you have, in terms of parallel, sequential, and random read performance, you can do something. So how would you read how would you actually read a file? So to read this file, how would you do that in RAID 1? Yeah? Yes, right. One of them starts from the beginning, the other one starts from the half, yeah, and then you assemble that in memory somehow, or I don't know what you want to do with the file, but basically, yeah, the second doesn't have to wait for the second half. Yeah? Okay, if your computer program requires that in sequential order, maybe it doesn't help. Yeah? But if you can process this stuff, for instance, in a database, filter, any where clause where you filter certain tuples, you may have one disk reading this part, the other disk reading the second half, and both start filtering already. So if the order doesn't matter, that's perfectly fine. So this increases the parallel, sequential, and random read performance. Same for random accesses again. You can distribute the random accesses over different disks for reading. That's fine. Writes, no gains here, because you have to, whatever you write, you always have to write it to multiple places. You change a block, you have to write the block to both places. So similar to the observation we had last time, if you always force a write down the entire storage hierarchy, you're switching off the storage hierarchy with respect to writes. Here it's kind of the same thing in a way that if you write something, it's the same as if you had one disk. It's the same thing. Even it's even worse, because if those disks have slightly different performance, you have to wait for the slowest disk to finish writing. So can even be worse. Yeah, but with RAID 1, you enter the game that you can lose one of those disks. And that's one of the main purposes of RAID. So RAID is also about performance, increasing disk performance. But the major use case is redundancy. Now, the problem with hard disks and other storage devices is that these devices may fail. So you may lose these disks. And what do? If your data sits on a single disk and the disk fails, then you're screwed. RAID 0, for instance, doesn't help in that regard. If you lose any of those disks, well, you have the odd blocks. Nice, okay, but the even blocks, they're not there. So what? You're probably screwed. So RAID 0 doesn't help with respect to redundancy, but RAID 1 actually does. It helps. So here you can lose any of those disks and the data is still available there. And that means in a working system, in a running system, servers typically have these disk arrays, and then it signals, oh, this disk is failing. And all you have to do as an administrator is to pull out that failing disk, pull in a new disk, and the RAID controller will handle all the magic, replicate all data over, and you're good to go. And of course, you can use more than one disk for this. But obviously, the more disks you use, the more space you will be wasting. Assume a disk array with 10 disks, and all of them have the copy of the data. I mean, it's an insane amount of redundancy. You may lose 9 disks, but maybe it's not a good trade-off. Therefore, there are other RAID levels, and one is called RAID 4. So RAID 4 works as soon as you have 3 disks at least. And the idea is, you do something similar like in RAID 0. You stripe the blocks over the disks, but just the first k-1 disk. So here I have 3 disks. And this should look familiar to you. That is like RAID 0. It's just striping, okay? But then what I add on top is 1 extra disk for parity. And those parity is simply a bitwise XOR operation. So this block is a bitwise XOR of blocks 1 and 2. That's the operations you're doing here. The block 1 XOR block 2 gives you this parity information. And the XOR operation has an interesting property that is, now if any of those disks fails, have I got this? So if any of those disks fails, you can reconstruct any block. So if you lose a parity disk, how do you reconstruct the data? You can reconstruct the parity disk, but the data is already there. So that's kind of, So I don't have to reconstruct data, but I can, if I pull out the parity disk, put in a new one, then recompute the parity using the existing disks. Job done. Right, okay, it's more interesting if you do this one. And then actually, for XOR, it holds if you XOR the parity, if you XOR parity 1, with the remaining disk, B1, XOR, what did I say as an operation? Also XOR, I wrote it out. XOR B1 equals B2. Hallelujah, that's fantastic. So basically any combination can be constructed as long as you lose only one of the disks. XOR is also used for these for this property of XOR. This is also used in computer graphic, or it was used, for instance, if you select something in an UI, sometimes it was used to XOR the selection area on top of the screen, yeah, and then you can easily remove it by XORing it again. Yeah? That's a very common operation in computer graphics. But here you can do the same. You just XOR and you're good to go. Yeah? And that holds for any combination. So any data disk you lose, you can reconstruct it by just XORing whatever remains together. Yeah? You have k disks, you XOR the blocks from the k minus 1 surviving disks, and you can reconstruct anything. Yeah? And that is an interesting property of RAID 4. So you can survive one disk failure. RAID 5, here the idea is, so the problem is here with RAID 4 that whenever you write something, you have to touch this single disk. Yeah, this parity disk is affected by any write operation. That's not true for if you write block 4, for instance, you only affect this disk. If you write block 5, you only affect this disk. You write to those. So the writes are distributed over the different data disks in this world. Yeah? But the writes are not distributed for the parity disk. The parity disk always receives the write, yeah? Because whenever you touch anything here on the data disk, you also have to update the parity. Otherwise, you would be violating that property. And that leads to something that's called wear. So this is used more often. You write more often to those disks. And there's a correlation between how often you write to a disk and the likelihood it fails. So these parity disks will fail more often because you write more to them. So therefore, there's a level called RAID 5 where the write load is distributed over the different disks. Here you say, okay, I don't always use the last disk for parity, but I somehow distribute the parity round robin. Yeah, it's a striping pattern from right to left. You can do it from left to right, doesn't matter. You just say parity is distributed round robin over the entire disk array. Yeah, that's the only difference. Other than that, it's the same thing. As with RAID 4, you need at least 3 disks, otherwise it doesn't make sense. Yeah, and everything else I said. And of course, you can use that for 10 disks, or 12 or 20, whatever you want to do. Yeah, and again, if you do the math, if you did 10 disks with RAID 1, yeah, that was RAID 1, replicate the entire database. Yeah, so you have a net storage of whatever 1 gigabyte, but you can, and then a gross storage of 1 gigabyte, but the net storage is just 1/10 out of that, obviously, because you replicate 10 times. 10 times the same data, not a good investment. But for RAID, if you do the same thing, there's just this one extra disk. Yeah? So if you have 10 disks, 9 out of 10 disks actually are used for net storage, and disk number 10 is just the parity stuff. Yeah? So with regards to how much data you store, you're much better off in RAID 5. With regards to how much failures you can survive, you're of course much better off in RAID 1, because there you can survive 9 failures. Any of the disks may fail. Here in RAID 5, 1 of the disks may fail. If you lose 2, you're screwed again. You know? So that doesn't help. So there are more RAID levels actually. But before going into that, maybe let's look at some code. Let's look at some code. So here it's in system storage RAID, and basically, so this is again a strategy pattern, and the idea here is that I have these logical block IDs as on the slide. Yeah? So each block has an ID, and then I want to compute the position of that ID in a disk array. So if you go back to the slide, what is the position? So the position is the disk. So it's basically the column. Yeah? Is it here? Is it there? Or is it there? That's the column, so to say. And the other is the row. Is it in this row or is it in that row? Okay. So basically a 2-dimensional coordinate system. And given the block ID, say block 5, for instance, I have to remove some of these things. Block 5, for instance, yeah, I now want to compute, okay, what are the blocks, the physical blocks affected. So block 5 actually, when I write block 5, that affects 2 positions, the data block and the parity block. The parity block also has to be updated. Huh? So this I would have to compute this one already marked and that one already marked. And that is what this Python program is doing for the different rate levels. So I have an abstract function that does exactly that. You feed in the logical block ID, you feed in the number of disks, that makes a difference of course, and then you return a list of physical block positions on the array. And the physical block position, as just explained, the disk ID, starting with 0 here, and an internal block ID on that disk, plus the information whether that specific disk should be a parity disk or not. Yeah? And these strategies I implement for the different rate levels. So for instance, if you feed in a logical block ID, what you return is, in rate 0, of course, you store the block only once. So what I'm doing is just a round-robin assignment here. Yeah? So I just say, okay, logical block ID, modulo number of disks. So any of those disks will get that block. That's the disk ID, and the internal block ID is just divided under integer arithmetic divided by the number of disks. And that will return this single block position. Actually, again, this exactly on the slide. So each block has one physical position. However, if you look at rate 1, so I have to replicate it, which means for all the existing disks that exist in my disk array, I return one block position. And that's always the same internal block ID. Yeah, because that's the same as a logical block ID. You have a one-to-one mapping. You also see that in the slide here. If you go back here in rate 0, yeah, so here the same IDs you have here. Those are internal block IDs now, and at the same time, the logical block IDs. It's the same mapping due to this one-to-one relationship. Yeah. That's why this is so trivial. But you return as many physical block positions as you have disks. Yeah? That's this list comprehension I'm doing here for disk ID in range 0 to a number of disks that has disk ID, a number of disks ID, many iterations. Yeah, I return one physical block position, and so forth and so forth. And if you run that, you can do that. What am I doing? There's a test for that in test storage, as far as I remember, and test rate or something like that. Okay. So here I have to enable this output. Maybe not this comment. And I run the tests. That's when you screw up. No, maybe 20 rows, or maybe a few less. No. Okay. Here, this is basically the output that we get there. So I try to stick a little bit to the notation I use on the slide. The striping pattern is not from right to left, but from left to right. So I start with parity here in the first row, and then the next gets a parity here. And this signals bitwise XOR, the XOR of 2 and 3. Not the IDs 2 and 3, but the blocks 2 and 3, of course. That's the content I'm storing there as a parity. Yeah. And then the test, if you look at the test, here I call this assignment function. I can pass a rate level, and for any rate level, I expect a certain output. That's basically what the test is doing here. So I have separate test functions for these different rate levels. They're commented. Nice. Okay. So that's a common anti-pattern in software engineering to comment your tests. You shouldn't do that. So the problem is you develop something And sometimes it's hard to get to the right position because with parallel tests and stuff, all kinds of things may happen. Sometimes the debugger is supposed to stop at a position, but it does not, and then it stops. All kinds of things happen, and then you comment tests. Yeah, I do that by writing an underscore in front. If you write underscore in front, the unit test framework will not consider this test function anymore. Yeah, then you fix your stuff, and then you forget to remove the underscore again. Not good, not good, not good. Yeah. So the right thing to do would be to not do it in the first place, or write at least a to-do. Yeah, that's was probably forgotten and it passed. Oh, it was even reviewed. Yeah, thank God it still works. Yeah? So be careful with that. That's all I'm saying. So sometimes it helps in debugging, disabling these things, but you should be really careful with disabling tests. It's really a double-sided sword. Okay, anyway, so I test all of these rate levels and then have this output function where you can specify the rate level, the number of disks, where you can do whatever. One more disk or 5 disks. 5 disks, what happens? Yeah, and then you see the same things. It's a parity over those disks. And if you do this for rate level 5, that will be round robin stuff over this. Yeah, and then you see the same pattern. Here the formatting is slightly off, but the idea is right so far. Parity over 4, 5, 6, and 7, and so forth and so forth. Yeah. So I invite you to look at this function. I think it clarifies a couple of things, how this actually works. So rate 5 is the most involved here. Yeah, I wrote a ton of documentation here and invite you to look at that because it really helps understand what's going on here. And you also see here in the return list, there are 2 blocks you're always returning in rate 5. Yeah, sure, same as in rate 4. There must be a data block. So this is signaled by this false flag here, and there must be some sort of parity block. Yeah? And both positions have to be computed somehow. Yeah, so much about that. Yeah, actually, this is kind of the asserts you should understand. These look like exam questions to me. Yeah. It's the same conditions as on the slides, actually. Yeah, so for certain rate levels, you have to have a certain number of blocks. So. Yeah, I think that's what I can say about this one. Okay. So, yeah, I implemented it for rate level 0, 1, 4, and 5. And if you look it up on the internet, you will find dozens of rate levels, but the most common rate levels are the 4 I just presented. So for instance, I think our server for our application system is run with rate level 5. Sometimes people also use rate 6. For that, you need a different type of parity. XOR is not enough. In rate 6, you can lose 2 disks, not only 1. But there are other ways to get features like that. And what you could also do, as usual in computer science, you can also nest the rate levels. Why not? Yeah? So this is called rate 1 plus 0. Or rate 1, 0. Be super careful with those names here. Yeah? Again, when learning for the exam or something like that, I'm using the convention that I name it bottom up. So if there's a 1 here, this means I start bottom up with a leaf and then I go to the root. But sometimes rate 1, 0 is called rate 0, 1. Be careful what people mean by that. Yeah? But in this lecture, it's always bottom up. And that means that you have here a subsystem. Yeah? You could say, this is a black box. You have no idea what the heck is going on here for the moment. Let's ignore what's inside the box for the moment. Yeah? I'm just saying, across those boxes, I'm using rate level 0. Rate level 0 means I stripe the blocks over those black boxes. Yeah? So block number 1 must go here, block number 2 here, 3, 4, 5, 6, 7, 8, and so forth. How I do that inside such a block, that's a different concern. And that's what I'm specifying here by saying, okay, that's rate level 1 inside a block. Yeah? In theory, you could even have a different rate level here for this block if you wanted. Yeah? So I'm just using the same rate level, and that's typically what's done, is the same level on the same rate level on the same level of the hierarchy. Yeah? You ask, does it have to be 2 levels? No, of course you can use 3 or 4 or 5 or 6 rate levels if you want. Does it make any sense? Of course not. Yeah, but you can if you want. So play with that. So but the most important levels, of course, what we will be seeing is a 2-leveled thing. Yeah, and then you can think about what what you gain in this anyway. Any ideas? So now we have that nice light, very colorful. Yeah, why? Why would I do something like this? Any ideas? What are the benefits? What are the drawbacks of that? How many disks can I lose? What is the storage overhead? Yeah?
Essentially, you can use 2 disks unless they have the same data, so you can lose the second and the fourth disk, for example.
Yes, exactly. You can use 2 disks. It should be the right disk, please. Yeah? That wouldn't be too great. Not good. Yeah? But if it's something like you're losing at the same time this one and this one, for instance, everything is fine because you still have this one and that one. So that's fine. Yeah? Very good. What does it mean for storage overhead? What's gross storage? What's net storage? Or what's the overhead, the degree of redundancy, however you want to phrase that? Yeah?
Essentially, you have 100% overhead,
Yeah.
the space that you really can use.
Yeah, it's twice the storage. Huh? Everything times 2, because each block is stored twice. That's read. Huh? What does it mean for read and write performance? What is the read performance here for reading a file? I read a file, I read all blocks. I don't have to have them in a specific order. I'm just saying I want to read all blocks from a file as fast as possible. What is the performance? Always this movement first, but okay.
I believe it will be like 4 times faster because first you can split between the blocks and then
Yes.
for each rate, like V1 and V3,
Yeah.
you can just one from the first disk and one from the second
Yeah,
disk.
yeah, right. For instance, here on the first disk could read B1, B3, second disk B5, B7. At the same time, third disk B2, B4, and the other B6, B8. Yeah? In general, yeah, like every 4th block is read by. I mean, you don't partition it per block. Definitely, you have sequential ranges to have sequential I/O, but basically that's the message. So read performance times 4. What about write performance? Throughput. Let's look at throughput. And compared to a single disk. Yeah.
It would be like twice as fast because
Yeah.
the rate one will have to write on both disks.
Yes.
Since we have 8, we can split it between this one is 2,
Right.
this 3, and this 4.
Right. So it's like having a standard rate 0 system, basically. The subsystems rate 1 don't add because with regards to write, they have to write it both anyway, so I don't get anything. Yeah? Correct. Huh? Okay, so let's invert that. Now this is rate 0 plus 1 or rate 0, 1. Now on the leaf, so before I had rate 1 here and rate 0 there, now I invert the roles. Now rate 0 is here, rate 1 is there. What are the performance characteristics? Let's look at, what did we start with? Did we start with, how many disks fail, right? That's how we started, right? So how many disks can fail in this world? And which one? Yeah?
We have 2 disks failing, but they have to be in the same order. So first and second and third and fourth.
So 2 disks can be failing, you're saying, and for example, let's number this from whatever 0, 1, 2, 3. So which can fail at the same time?
Either 0 and 1.
0 and 1, if they fail, I still have, yeah, the entire thing here, so everything is fine, yeah, correct. Other options?
Or 2 and 3.
2 and 3, same thing, sure, mirrored, yeah.
Or maybe 1 and 2.
or maybe 1 is failing and 2 is failing. Yeah, so that was a lucky one, because here now I have this odd blocks here and the even blocks there. Yeah, and there already we are in a system issue, because to get that information, I mean, if you consider this a subsystem, or if you consider that a black box in a way, yeah, and the black box is saying, yeah, one of my disks is screwed, and this black box is saying, okay, one of my disks is screwed. So in this situation, you can only reconstruct if you semantically understand which of those disks actually are screwed to be able to reconstruct. So that's again an interfacing issue here. Yeah? If the RAID controller doesn't have full control over the assignment, you might be screwed. Yeah? Okay, performance-wise, so what happens here? Let's keep the index number. So what did we start with? Read performance. What kind of read performance can you get? Reading a large file? Any difference to what we had before? No, maybe you?
It's the same as before.
Yeah, same as before, right? Times 4. Write performance? Same as before, times 2, yeah? Because again, you have replicas here. So you gain, if you write block 3, for instance, here, you have to write them there at the same time. So you don't have effect, you don't have an effect by having 2 disks with regards to that. Yeah? But of course, you can concurrently write block 4 also twice, but again, you have a times 2 performance improvement. Times 2 because I have 2 disks here in these subsystems, because on the higher level. Yeah? So you always have to consider, okay, how many disks or how many subsystems do I have? And how many disks does each subsystem have? So that determines the performance gains and number of failures you can survive. Okay, yeah, with that, let's look at another important property of memory. And this is, again, a trick that's played multiple times in the entire storage hierarchy. So similar things happen inside a hard disk, inside the operating system, inside an SSD. Yeah, it's always the same trick, and it's one of the most important tricks in computer science is to introduce indirections. If in doubt, introduce another indirection. That's always the silver bullet, and it's the same here. And that's a very good idea. And it's used all over the place, like all operating systems do that in one way or the other. And the idea is, when you operate with memory, you have these memory addresses. So we don't really see that in Python. But in C++ you see it. Yeah? You have this pointer and you look at the number, and that's the number into the memory. And it really gives you an address. Yeah? And it really feels like low level, even though it's not. Because this address doesn't really exist. It's just a virtual address. It's not an address that the computer system uses to access the stuff on the physical DRAM. No, there's an indirection in between. And that's called a virtual address or virtual memory management. Yeah, so whenever you specify a specific address in your C++ program, the operating system will translate that to a physical address. Yeah, and that's what the operating system is doing. So the physical addresses are shielded. Yeah, they're protected. That has the effect that, in particular, 2 users or 2 processes on the same machine cannot get in conflict that easily, because virtual memory can make sure that not the 2 users write to the same address. Yeah? So basically the idea is that each process has its own virtual memory space. Yeah? And then that is somehow mapped to physical addresses. Yeah? Okay, but first things first. So I will explain that history of that idea with something that's called shadow storage. Yeah? And that will then lead to why virtual memory is doing that. So in shadow storage is the idea you keep 2 versions of each modified page or block. Again, similar a little bit also to what we did in MVCC. Yeah, we have transactions operating on this work in progress stuff, and only when you commit it, you put it to the committed list. Yeah, very similar thing here. So you have 2 versions of the block. Rather than having just one block, and you write something and then you crash and you don't have the block at all anymore, you keep one copy in a way, yeah, and then you write on some other version of that. We're not sure whether that will make it to become the final version. It's the same idea. That's all over the place in systems. And then you have an atomic switch to indicate the currently consistent versions. So to make it more concrete, basically you have these physical pages, and then you have a mapping. So this is already a mapping like, okay, you have a logical page ID here, so the user refers to some position here, and that is mapped internally to physical pages. Here is our indirection. So you don't operate directly on the pages that you have in your system, but you operate on the indirection. If I say I want to have page 42, the system will say, yeah, there, you mean 13, right? Internally, for me, that's page 13. You don't have to know about that. I just give you the contents. Yeah, but if you say 42, it means 13 right now. Maybe later it means 14 or 15 or 16. The user doesn't have to know. It's just an extra indirection for those page IDs. And yeah, what you have here is this indirection, and you have one transaction operating here on those pages, and you have a pointer to the consistent version saying, this mapping is currently the consistent version with regards to transactional properties. Now if a transaction comes in and says you want to modify, you do that on a separate version. Basically you copy the mapping, so whatever mapping you had from this space, from those pages, these virtual page IDs to the physical page IDs, you see the arrows are exactly the same. They're just mirrored. Imagine this were a mirror. You mirror it over to, you do a copy of the mapping, not a copy of the pages. That's important to understand. So I'm not copying the contents here. What I mean by that is really, this is not the contents of the pages here. This is just an indirection. The actual contents sit here. And now if you access anything, if you want to access any page, you go through the mapping, but eventually you touch upon the data that sits here on the physical pages. It's just another indirection to protect the physical pages from concurrent accesses. Yeah, and in this world, you can basically have a consistent version. That is your consistent version mapping to the pages that have the consistent data. And now any transaction that starts and does something could operate here. And now, for instance, you insert something. You insert an update into a new physical page B6. Then what you do is, okay, now this arrow, which previously pointed here, now points to some new physical page. That's a copy of the old page. Basically, you copy over the old contents, and then you modify that page. But from the point of view of this transaction, it doesn't even notice, because the logical ID is still the same. So if this logical ID, I mean, if I number them, whatever, 0, 1, 2, 3, this is logical ID 3, that now points to this block, and before it pointed to the block adjacent to that. Yeah, so logically, I didn't change anything, but internally, I represent it by a different block. Yeah? And that is what you can do in this world here. Yeah, here another page is changed. Now insert update into new physical page B1. Yeah. Now, if this transaction crashes, all you have to do is you throw away that page mapping. That's happening here. Yeah? So you still have this consistent version on top, so you didn't lose anything. In particular, didn't lose the committed versions of those blocks. Yeah? Didn't screw up the state of your database system or of your pages if you use this outside the database system. Everything is still fine. But if you commit, you persist the changes. And how do you do that? You simply switch the pointer over to this version. You're saying, okay, this is now my new version. Yeah? The old version, the old mapping is not up to date anymore. From now on, I will be using this version, this mapping underneath. And if a new transaction comes in, it's not shown here, you would have to copy over this mapping to the new transaction. Yeah? And this is a mechanism that's actually available in operating systems that's called copy on write. Copy on write. I will show you another example later on. Also cow for short, like the animal cow. Copy on write. So the idea is those two transactions share physical pages or blocks, however you want to name it. They share the data for stuff that's only read, but they don't share the data for the stuff any of those transaction writes. Here, in this technique, this consistent version may not be written to directly. That's the read-only version, so I can only write here. I can modify blocks here, but whenever I write a block, and that block still points to a shared version of the block, I first have to copy the block over, adjust the mapping, and then I'm allowed to write. And this is called copy on write. On writing, you copy over the block. And you only have to do that the first time, of course. Yeah? The next time you write to this block that is already copied, you don't have to copy it again. That would be stupid. Yeah? But just to make sure you're not writing to the block that's shared with the other version, with the other transaction. Yeah? Then you copy it over. Yeah? And that's called copy on write. And that's something you can do because you have these indirections. Yeah? If those transactions would directly operate on those, had a block space here, yeah? If the transactions would be referring directly, for instance, block 1, block 2, or something like that, yeah, they could override each other's changes. And through the indirection, you have an extra mechanism to protect transactions from each other. Yeah? And that's a very important mechanism in operating systems done through virtual memory management. So let's look at how this is actually done in virtual memory. So virtual memory doesn't have this pointer to a consistent version, but does something very similar with those indirections. This is again the pros and cons. So you only double the storage for the changed pages, but I said that undo of changes is easy. Helper data structures, yeah, whatnot. Yeah. So this is what you see in virtual memory. And basically it's an addressing scheme that uses a prefix and a suffix. So the idea is you have what's called a page table that maps from the virtual page ID to the physical page ID. There's an internal physical page ID. This means these physical pages you don't see as a user. That's done internally, handled by the operating system. What you see are those virtual page IDs. That's what you are referring to. And an address in computer memory is always a combination of this virtual page ID plus an offset in that page. Because if you think about that, that's how you address anything. Yeah, if you address if you address any byte in computer memory, and this is your computer memory, and that's partitioned into pages, and now you want to address this position, I mean, you can say that's the page plus the offset in the page, so the number of bytes in the page till you get to that position. So these two keys form a primary key, so to say, a composed key that once you specify, that's page, let's make that physical page 5, 6, let's make it virtual, whatever, doesn't matter. So that's your virtual page ID. Yeah, you specify something like 6, and whatever the offset is here, whatever, 124. So basically the address of this block is 6, 124 in virtual space. And now you squeeze these two numbers into one huge integer, yeah? Typically 64 bits these days, and you say, okay, the prefix of that integer, that's actually my virtual page ID. Yeah? That is what 32 in this example, and the suffix is the offset within the page. And what the page table of the operating system will be doing is, you believe that is your page, no, I will replace that by something like that. Yeah, so the prefix is replaced by this page ID mapping, hiding the fact that the addresses underneath are different. That is what virtual memory is doing to those addresses. Yeah? And you can map that to an index. Here, for instance, a one-level tree. So this is actually called a trie, as it partitions the data space. But basically here I have a 4-array tree. And each of those subtrees reflects one prefix of 2 bits in that address. Yeah? So if the yellow part is 2 bits, I have 4 different subtrees, 4 different 4 different combinations I can assign to that, 4 different numbers, and that's the 4 subtrees. And of course, you can recurse like that and go on. For instance, you could say, okay, I have another 4 bits for the second level of that tree. 4 bits means 16 different values, and that's exactly what you're seeing here. Yeah? And then here within such a cell, that might be the actual page. And that's how you map that to a trie. And this copy on write pattern is the idea that given some physical memory partitioned into units, pages / blocks, and you allocate or write and, or insert or do update operations on those units, is you hide the physical addresses and make users share the data whenever possible. And only if there's a conflict with regards to that data, you copy on write. You separate the versions. Yeah? You can all read from the same versions, that's fine. But if anyone tries to modify, that user has to have their own copy. And that's called copy on write. Only when you try to write, then you create the copy. You don't have to do that before. So when thinking about file systems, does any of you see a use case for that? Consider a file system on your machine. It keeps all kinds of stuff, right? All kinds of files you're working on. Slide set 09A. This is 09A is stored there. Incidentally, you copied it. You have 2 copies of that file and you moved it to the folder. Oh, you didn't move it, you copied it again. So 3 copies of the file on your disk. Oh man, why do we have that? What does it have to do with this stuff? Any idea? So you have the slide set for this lecture. I think we're in 09A or something. No, we're in 08. We're in 08, right? Slide set 08. Ah, okay, I'm still in 08. Okay, at 9A I uploaded this morning in 9B. Okay, so 08, that's the slide set 08.pdf. That's the file, that's a couple of blocks, okay? I don't know how many, couple of blocks. So here's my blocks. I partition it into blocks. Whoops. And you put that on your file system. Now you copy. Incidentally, didn't meant to do that, but when there's a download folder, now you copy it over to another folder, you were meant to move it, you copied it. Now you have another copy on your file system. You have that open now in this lecture, and you want to annotate it. You want to annotate it with information. What the heck is the professor currently explaining? I have no idea what professor did. He is currently explaining. Write the annotation on the PDF. Yeah? You save it. Yeah, so which means you modify this block. Huh? Or another block here, you say, oh, this explanation was so awesome, and this is unbelievable how Professor Dittrich is explaining that. That's another annotation. I don't know. You choose whether you do this or that or both, whatever. Sometimes I hope I explain these things. Yeah? Okay, so you store that, and maybe you modify the block, so you have these 2 files. What does that have to do with this stuff on the slide? So then let's number the blocks. I have 5 blocks here, right? So this is block 0. 0, 1, 2, 3, 4. And same thing here. 0, 1, 2, 3, 4. So the file system stores this stuff, stores these 5 blocks and those 5 blocks. What would be a different way? What would be the copy on write way of doing it? That's the file system. Okay, how would we do it under copy on write semantics? So we have our slide set downloaded. We have those 4 blocks. And now you copy it over from your download folder to whatever folder you keep your lectures in. Now what? What happens? Yeah?
You actually copy it over, but just like create reference or something like
Yeah, right.
And then you only copy the blocks you annotate.
Right, so I create kind of references. So I make it with a dotted visualization here. So basically I'm saying this points here. Okay. Now you're in the lecture annotating this with that information. You want to annotate this, hey, this is really an awesome explanation, you know, right? Cool. What happens?
And at this point you only copy the memory over.
At this point you actually copy it over. I have to picture different frames for the video recording. Come on. At that point, you screw that pointer and say, yeah, oh, I really need a copy of this. Yeah, you copy over this stuff. Boop. Yeah, that's one operation. Copy on write, because you want to write. Copy before write would be the better name. You first copy and then you write. And then you write your annotation here, whatever. So this is really now a copy. This block is a copy of that file, but everybody else here is just pointers to the existing stuff. Yeah, that's a copy on write pattern if it were done by file systems. What do you gain? What do you lose by doing something like that? If you did that on a file system, what do you gain? Or maybe someone else, yeah.
I mean, if you mostly store copies of the same data, you save a lot of space.
Right, you have to transfer less money to Apple computers, yeah, or whatever, where you buy your stuff, yeah? Because each block is only stored once physically, everything else is references, yeah? If you blindly do that and really copy the file physically, yeah, what do you lose? You gain, you save space, yeah, that's true. But what might you be losing? Yeah?
So we may create overhead stuff when we access a modified block and we have to
Yeah.
avoid the usage.
There's no free lunch. That's the no free lunch argument. So every indirection creates some overhead. You have to maintain those structures, redirections, stuff like that. Fair. That's a fair argument. That's true. I'm not sure whether that's so much these days, but there's overhead for keeping these mappings rather than directly accessing the blocks. That's true. Some other drawback anyone is seeing? What am I losing? I'm gaining, I'm losing. Most computer science decisions are like that. I gain something, I lose something. It's rare that you only gain. There's always a price you pay. Yeah?
You're losing the redundancy. So if you lose the original file, then you don't have to modify it anymore.
Right. Any of your application programs, yeah, maybe this block here is shared by whatever 10 different files. Yeah? If any of the application scrambles that block, destroys the block without first doing the copy, however that will happen. Yeah? But assume there's a scenario where you don't copy first and then write, but you write to this block that's meant to be read-only. Everybody loses that block. Yeah? So implementation-wise, you would do that you really forbid write access to the block before without copying. Yeah, that's an easy way to protect that. And what I'm aiming at is really, that's called, it leads to a technique that's done in file systems or in large data collections that's called deduplication. Deduplication. Deduplication is exactly doing that you somehow, I mean, you can do that on a file level, you can do that on a block level. Deduplication. That means you get rid of the redundancies. It could be that all files that are exactly the same are replaced by references. If you think about in Unix file systems, you have these soft and hard links. That's basically the same thing. Yeah? That's a reference to an existing file. Yeah? Or you do it on the block level. Yeah? And then you replace those file physical copies with a reference to the original file. That saves a lot of space, of course. This is the inverse operation to copy on write, in a way. Yeah? Because is that even true? Is that the inverse operation to copy on write? By copy on write, I split. Deduplication, basically, I'm reconstructing the pointers. Yeah? Basically, after the fact, even though basically it's in this world. Yeah? In this world, you created a copy, and then you found out, oh, it's the same thing. So deduplication would say, aha, now this should be dotted. Yeah, it's basically trying to reconstruct what should have happened by using copy on write in the first place. That's what you're doing by deduplication. Removing physical replicas and replacing them by references. Super important pattern all over the place in systems. Okay, you can also do crazy stuff in query processing with that, but that's a different story. Yeah, advantages: save considerable storage space. You might be managing overhead for page tables. Fragmentation. Fragmentation means that data is scattered all over the place in the storage medium. Not a big concern these days anymore. Yeah. Okay. Yeah. To wrap up, what I wanted to show you is that's also a weird artifact in the computer science literature that people talk about the storage hierarchy, and these graphs, these textbook graphs were done when there was no internet, interestingly. Yeah? So that was 70s, 80s textbooks. But if you think about what the storage hierarchy actually is, yeah, why isn't the entire internet part of that storage hierarchy? Because if you access anything on the internet, I mean, even if you watch a movie, for instance, yeah, you go to Netflix, watch some movie, and you retrieve that stream of that movie from somewhere. And of course, the internet has a caching mechanism. This is called CDN, content delivery. Oops. That's a bad place to write, maybe. CDN, content delivery networks. So when you ask for a stream, and it's not that stream will be delivered from a server in the US from Netflix headquarters, of course. No. They have copies all over the globe, of course, for all of this content. Same for YouTube, for all content providers do it like that. So if you sit in Saarbrücken, the stuff will probably be served from a server in Frankfurt. I guess there's stuff even in Saarbrücken somewhere cached, yeah. So you don't have to go all the way to the server in the US to fetch that blockbuster, so to say. That's the same thing here. Stupid joke, but fits, yeah. So it's a caching hierarchy. All of these servers form a caching hierarchy in a way. They store part of the data from the stuff underneath. The same techniques apply. So if you work with CDNs, or whether you work with database buffers, or you work in hardware with buffering mechanisms of the L2 or L3 caches, the same techniques apply. Same stuff, different names, absolutely the same stuff, same algorithmic problems. And that's very important, a very important takeaway message, that the storage hierarchy is actually, also you can, everything you do on the internet is part of that as well. Okay, and finally to wrap up, I wanted to show one thing that has been popping up a bit more recently. So we have this von Neumann architecture where there's a computing core and there's a memory and there's this weird storage hierarchy with all kinds of storage layers. But there is considerable effort to marry computing with memory. Yeah, so to not have the strict separation of memory and a computing core, but to somehow spread, enrich memory to do some computing as well. That could be very lightweight computing, but some computing, yeah? Because in the standard model, it's always like in the standard storage hierarchy, whatever you do, you always have to transport stuff to the core. There you can do some computation. There's the arithmetics you can do. There's the logic you can do with your data, and then you write the stuff back. But that means you always have to transport stuff to the core to do something with the stuff. In contrast, if you were able to do some of the compute in memory already, then what? What would I gain? Assume you're interested in a specific book, yeah? And you really have to select which book to read, yeah? And then you ask our computer science library, or could you please bring all your books to this lecture hall such that I can select the book that's interesting to me? Would you please do that? It's probably only, whatever, 20 trucks. Bring it here, and then I take one of those books, and then you bring everything else back and put it into the shelves and stuff like that. Is that a good strategy? They won't do it, of course, but yeah.
So it's like you can filter out from the data itself, so when the data is into the core, it's only part of the memory.
Yes, yeah, that's the idea. So I filter out, so filtering is one use case, but it's the most important one. So you filter out stuff you're going to reject anyway. So why the heck do you even transport it to the computing core? It's just in the way. It's just on the road. It just allocates trucks and its transport costs. And you have these transport costs in computer systems in terms of bus systems, memory systems. Yeah, you have stuff to transport to the core. And that is very often the bottleneck, interestingly. So these systems are often not halted or slowed down by the computational power. That's the problem. But the stuff of data, you have to transport to the core. And that means, and there's a term for that, that's called memory-bound. Memory-bound computing. Memory-bound. And that means that, oops, what's going on here? So I'm at the boundary of the slide. Let's write it here, memory-bound. And that means, the memory is somehow in the way, or the transport mechanisms, the transport hardware is in the way. It's not the CPU. The CPU is just waiting for data to process on. And you could improve such a system by pre-filtering stuff. The more you pre-filter in memory already, the less you have to transport. And then you don't have such much pressure on the transportation system. You don't need 20 trucks, because if you tell the library, hey, bring me this book, someone could walk over and bring it to you. So, of course, no one would bring a book to you, but if I say, could you bring the book to you, they would also say these days, no, you can fetch it yourself, Professor Dittrich, you know where the library is, right? Why would I bring a book to you? Are you crazy? But you get the idea, So it's less transport costs. And there are a couple of devices allowing you to do that, actually. What did I want to say about that? If you're interested in that, so there are two very good overview papers I bumped into. One of my PhD students found that actually, as we did the research for this lecture. It's pretty interesting stuff, but it's probably more for very high-end scenarios. So for standard database systems, you won't need this stuff. But for very high-end scenarios, that's also a cost factor. That may be cheaper to buy the super-duper hardware that can pre-filter memory rather than having the standard storage hierarchy and then having to transport a lot of stuff. You might get better performance numbers, actually, with stuff like that. Okay, that's so much about storage. Yeah, maybe let's go briefly through the summary. So properties of the storage hierarchy impact query processing efficiency. Yeah, and at the end of the day, we want to process queries. So we have very similar tasks across all of those layers, as you have also seen in the implementation I showed. Maybe we can go back to the implementation again briefly. So we should think about read strategies. What do I read when? So in the sense of on a storage layer, yeah, when you read from a layer below, you have to decide what to evict. That's an important strategy. And that means also what to write down if that was a dirty page. Yeah, so all of these strategies play a role in performance, because if you take the wrong turn here, take the wrong decision, you might be impacting performance in such a system. For hardware, it's important to factor in random versus sequential I/O numbers or performance characteristics of the devices. And it's important to think about, okay, how can I split up my storage layers or my compute layers? NUMA being you have non-uniform memory access and you have multiple CPUs on your board. More important for databases is RAID. You split up the storage layer into multiple disks or /SSDs. Right. Yeah. And maybe we can briefly look at, I did a little modification to the storage layer stuff I showed last time. So basically we had this test where I had the storage layer and showed you this buffering property of the storage layer. So we have a DRAM and we have an SSD, and the DRAM has a link to the layer below. And that is basically what a database buffer would be doing. Yeah? So you have the database buffer controls which pages are loaded into main memory and which are not loaded. Which pages are evicted if the memory gets full. Yeah? Does the page have to be written back because it is a dirty page? It was modified somewhere. You don't want to lose that information. And that's basically what you model through something like that. Yeah? And if you execute that, you see, I still have this RAID enabled. I should disable that. You see, yeah, this is a storage layer DRAM, and this is a storage layer SSD. And what I modified slightly to do this prefix addressing. I explained it with virtual memory. So over last lecture, I changed this to allow for different addressing schemes. So if you think about what main memory actually is, main memory is kind of a key value store because you ask for a specific byte and you want to have the value of the byte. It's a key value store. But if you ask a storage device, you ask for a page ID, and that gives you 4 kilobytes already, a much bigger chunk. So it's a different address space. And this leads to that you could pass an address conversion strategy. So how this works is that on one layer, maybe let's go back to the test that explains it a bit better. I think I have an extra test for that. Yeah, this is this prefix addressing. Now I want to have something like that in DRAM. I have byte addressing versus in the storage layer underneath the SSD, I have page level addressing. That means those two layers operate on different address spaces. That means if I specify a specific address in DRAM, I have to translate it. So maybe let's go through the test that makes it clear. So basically, I add 4 pages here to the SSD. So that's the page ID, and that's the contents of that page. The page size is only 4 characters, symbolizing 4 bytes, would be much bigger in reality. And then on the, I use a prefix addressing scheme that says, okay, the first digit is the page ID. So basically like on the slide we had here, same idea here, like on this slide. Yeah, so this is a prefix, that is a page ID, and then that is, the suffix is the offset into that page. That's what I'm implementing here. So if I say 2, 1, that means page number 2 and offset 1. which should give me the 9, because this is 0, this is position, this 9 is at position 1 exactly. That is the byte I should get. The same here, if it's page 3, offset 3, that should give me this dollar symbol, and so forth and so forth. So the DRAM speaks a different language than the SSD underneath. And in the output, you see that the storage layer now buffers individual mappings for 1 byte. So it maps this address to this content of that address to this byte, whereas the storage layer maps entire pages. So now in the get method, if you go down to, go here, in the get method, in DRAM, you're asking for a specific 2-digit address. You first do the check, oh, it's not in my storage. Okay, then I have to do something. I have to ask the layer below. There's no layer below. Okay, I'm screwed. The data is not there. But if the data is there, you have to translate the address to the language spoken by the layer underneath. And that means I have to just show the prefix to the layer underneath, because the layer underneath doesn't care about the offset into the page. So I need to run the address I'm asking the DRAM layer about into the address the SSD can understand, and that is just the prefix. And that's what I'm doing here with this conversion strategy. This conversion strategy just splits, maybe there's a here, that is how it is defined. It splits the given address into 2 parts, the prefix and the suffix. So when calling on this method, I can basically get the prefix address for the lower layer below, and I use that address to query for that particular page. Here I get that page, and then in this layer, in my DRAM, I just put the specific byte I'm interested in. So and that I'm doing by using the offset here. So the addresses are used here as strings, so I have to still do the int conversion to get the offset into the string, which in Python is a list, of course. So you can reference every character by its offset in the string, and that's what I'm doing here. So I create a copy of this byte in this layer. That's the idea. Of course, DRAM doesn't keep these fine granular mappings, but if you look at the caches in the computer architecture, they have something that's called a cache line, 32 or 64 bytes, smaller chunks that do exactly the same thing. So you don't keep the entire page in the caches, but just a subset of that page is copied into the caches, and then it can be referred from the outside. So it's a bit oversimplifying and abstracting it a lot, but the core idea is the same. And in the test, when you look at the test again, right, that's what you see in the output here. So maybe I invite you to debug through that a little bit back home. I think you need to debug that to understand. Why isn't this? So only when I execute and okay, I got it. Then you see, so you have pages here that are being mapped here, but here you only keep those references. Okay, yeah, that's something I wanted to show about that one. Any questions about that one? No? Takeaway for you is the storage layer implementation is really, that's exactly how you implement a database buffer. Of course, you don't implement the storage layer yourself. It's all there, the hardware does all of that, but there's this one point in the storage hierarchy where you have to be careful, and that is between main memory and external storage. And that is where you have to do something and make decisions in a database system, and that is where you implement a database buffer using these kind of interfaces here. Okay, so much about that. So we still have some time to start with the next topic. So now we talked about the storage hierarchy, and then we can now think about, okay, what does it mean to run algorithms in such a storage hierarchy, actually? Yeah, so, and then I have to go here. So I will show a couple of slides along the lines to explain that. But typically, when you talk about algorithms in the storage hierarchy, you can ponder, you can think about the performance metrics, the performance characteristics of those algorithms. Yeah, there are actually only three classes of performance considerations. One is complexity. I like what the theoretical computer scientists do. Maybe make that a little less extreme here. Something like that. Yeah, so you can, say that is the complexity of my algorithm in the best, average, and worst case. And it's a very important coarse, granular information about an algorithm. But you could add more. You could also vary about the constants. So the constants in the individual operations are typically not considered in these complexity analysis. Yeah, so that's something that's very important when you really want to understand, okay, which algorithm is faster, or which algorithm, even though this has, you have two algorithms that are linear. If one operation for algorithm 1 takes 1 hour and the other takes 1 nanosecond, well, there's a performance difference. Yeah, they're both linear. Who cares, right? But that's quite a difference. Yeah? You want to know about that. You should factor in those constants. And in database systems, we need to factor in these constants. So. And then the third option is the third thing you could do is you implement stuff and benchmark it. Yeah? But now this is all without storage. Yeah? Even for algorithms that don't care about the storage hierarchy, it's more like about some computational problem, you still have these three dimensions, so to say. But now we're adding storage and things get way more complex. Yeah, so we have to consider the costs for reading and writing from or to storage. And again, that's typically the thing you optimize on in a data-driven system, in a database management system. It's not so much the computations. Computations in our world are typically so cheap that they are not in the way. What's in the way is memory, handling memory efficiently. That's the art. Yeah? And there are certain performance dimensions of an algorithm. So the performance of an algorithm can be analyzed along many dimensions: runtimes, wall clock time, clock cycles spent, I/O operations performed, robustness for different workloads. Yeah, we had that when we talked about RMIs. Yeah? RMIs are overfit towards a specific distribution of your data. They're not so flexible when that distribution changes. So those index structures are not that robust. But they have advantages if you know that the shape of the distribution doesn't change. Adaptability to different workloads. That's, for instance, something where B-tree shines. B-tree will work for any kind of workload. Maybe it's not the best performance in the world you are getting, but it's very robust no matter what you insert into the tree. Read versus write performance. Yeah? Are you reading mostly or are you writing a lot of stuff? That may lead to different design decisions. And so forth and so forth. And there are only three ways to analyze performance in any computer system, or three classes. And one is the analytical model, so some sort of mathematical model. Could be complexity or a cost model, something predicting the costs of an algorithm. So cost model versus complexity, again, is cost model is adding the constants. Yeah? It's also factoring in constants. The second is simulation. So you simulate your algorithm somehow, the effects, what it would be doing, and you try to simulate the performance characteristics. And the third is running an experiment. Experiment meaning you really implement the stuff in the best way possible, in the most realistic way possible, with real queries, with real data sets. If you get access to that, it's a different story, but that's what you should be doing. And that's important to keep in mind. Whenever in your future, you will hear people say, okay, this algorithm is bad because the complexity is bad. Yeah, okay, that's one dimension. But what about the other dimensions? What does it mean for wall clock time? Yeah? What does it mean for a real experiment? Is it really so bad? Can I live with that complexity because my data set is small, so who cares? Yeah? Or is it something to consider? So we have these 3 dimensions, and it's important to keep in mind that none of those dimensions is better than the other. They have different properties. It's super well explained in this book. Yeah? So if you're interested, it's a very old book. It's available in our library, but that explains the art of computer systems performance analysis, because often sub-communities of computer science focus on certain areas. Yeah? Theory people would focus on that. Analytical model, for instance, yeah, whereas more practical people would focus on experiment. But you can't say that one is better than the other. These analysis techniques serve different purposes. Yeah? And the visual representation is something like that. So here you have these 3 methods. So analytical modeling, yeah, cost models, or complexity is relatively easy to do, not in all cases, but in many. So the effort is low. It's not really down to earth. It's far away. It's abstracting from a lot of information. But however, it has the advantage that you can generalize it. Yeah? No matter how you implement that algorithm, the complexity class will be the same, unless you do something wrong. Yeah? But whether you implement it in Python, C++, Rust, whatnot, yeah, it's the same analytical model. It's the same complexity class. It's unchanged whatsoever. Yeah? So it's very generalizable. That's a big advantage of these methods. Kind of the other extreme is an experiment. Typically, a lot of effort required, very down to earth, and it's not so generalizable because you make decisions. You say, yeah, I use this programming language, I use that database system, I use that data set, I use those queries, and it's whatever, Frank implemented it. And maybe he's not such an experienced programmer. Yeah? If Peter had implemented that, we would be getting way different performance numbers. So the guy who implements it or the woman who implements it makes a huge difference, of course. Yes, you can't be sure. It's a huge hassle when comparing algorithms that were implemented by different software engineers. Can be a huge difference. Tiny mistakes can add up like crazy. Yeah? So generalizability is not so cool. Simulation is kind of the middle ground. Yeah. So yeah. Depends on what you're simulating, but if you're simulating performance, that can be a good trade-off, actually. It's like a middle ground of analytical modeling and experiments when it comes to down-to-earth, reflecting reality. And generalizability is higher, typically, from a simulation, because you can abstract over the programming language. You can abstract away the database system and certain properties of the data sets. Yeah. So that's something you should keep in mind, and that's something we will be continuing next week. On Wednesday, we will continue on Wednesday. Friday is more like a repetition, kind of summary of part 1, and then Saturday is the midterm. Yeah. See you next week on Wednesday.